if B bar minus C bar is an element of BMK. If the difference of two M chains is a boundary, they're said to be homologous. And so that defines, in fact, an equivalence relation. You can say that, you know, B is homologous to C if and only if, you know, the difference is a boundary. And that defines an equivalence relation on the set of M chains. And so you can look at the quotient space. All right, you can look at the quotient space. Well, let's see here. I'm missing one thought. I think there's something I haven't said yet. Oh, what would this mean? I think I may be not saying this right. Oh, I'm sorry. I wasn't supposed to say, I know what I've done. I know what I've done. I know what I've done. Sorry. My bad. This is not supposed to be chains. This is supposed to be cycles. We're supposed to talk about whether or not two M cycles are homologous. All right. So the equivalence class with Z bar not in it is Z bar a cycle, an M cycle in K such that what? Z bar minus Z bar not is a element of BMK. How do I know that the difference of, well, let me say this a different way. What's the relation between ZM and BM? Is there any kind of relation here? I feel like that's the thing I haven't said yet, and I really probably should have said it already. How about this? If C bar is an element of BMK, then C bar is equal to the boundary of C prime, right? Thus what? The boundary of C bar is what? Which is 0. Yeah. So what does that say? That says right. So every boundary is a cycle. However, not every cycle has to be a boundary. These aren't equal. There could be a cycle which is not a boundary. It's possible. Definition, HMK K. This is the mth homology group of K, is defined to be the quotient vector space of cycles, m cycles over K, by boundaries over K. So this is a quotient vector space, which makes sense because, well, the M is a subspace of Zm. The dimension of the mth homology group over K is beta M, which is the so-called Betti number, the mth Betti number. Mth Betti number of K. So, to calculate the homology of the space, we have to do what? What does it take to calculate the homology groups of a space? You have to get your paws on a triangulation of the space, and then you study the chains, and you figure out which ones are, you know, you have to figure out what's the kernel and the, well, I mean, there's something else I could write here that I haven't written yet. Let's see here. If where'd you go? If we were to look at Cm plus 1 K, and then the m plus 1th boundary map, you notice that we really have more than one boundary map, right? Because we have a boundary map on chains of different size, yeah? So if I add a index to it to indicate which one I'm talking about, it's productive for a discussion like this. We have this long exact sequence, well, whatever that is, sorry. We have this diagram of vector spaces corresponding to the m chains, m plus 1 chains, m minus 1 chains. And he writes the following. He says alpha m is equal to the dimension of m cycles. And that is going to be, by the rank nullity theorem, what? I mean, we define the boundary map just not just on cycles, right? We define the boundary map on all chains, right? What's the significance of cycles to the boundary map? What's another way we could define ZMK? It's the kernel of what boundary map in this language? Kernel of partial M, right? And how about this one? BMK is what? It's the image of what map? It's the image, partial M plus 1, in my lingo. I mean, in Ratlin's lingo. But if we apply rank nullity, the rank nullity theorem, right, the dimension of this vector space, CMK, is the dimension of the kernel of the map partial M, right? Plus what? The dimension of the image of partial M. But this is also what? the dimension, like the kernel of partial m is the what? It's the dimension of ZMK, right? And this is the dimension of what? B, M, you say minus 1 or plus minus 1, right? What's the, quotient vector space linear algebra, which of course is making me lots of friends with this semester right now. What's the dimension of HMK? Well, something I said today in linear algebra, which no one thinks matters. Well, maybe some students do. I don't know. I'm not convinced. DM, that they care. ZMK, I hope I'm wrong, minus the dimension of BMK. So this is the dimension of a quotient vector space. It's the dimension of the ambient space minus the dimension of whatever you're squashing to 0. So if you look at that, and of course this is the Betti number. So if you can calculate the dimension of the kernel of the cycles and the dimension of the boundaries, you can figure out what the Betti number is, which essentially tells you what the group is here, because these will just be vector spaces at the moment. Well, it doesn't have to be that, I suppose, but no, I think it does. These are vector spaces, so it's just going to be like Rn, R2 in the current setup. But you see, you can figure out what the dimension is of the cycles and the boundaries by using this and doing explicit calculations, right? Now, that might not be obvious. I mean, it is actually serious calculation. Let me show you. Let's do the circle. Let's try the circle. So we'll start with the zero chain. What's the zero chain look like on the circle? I need to find myself some space to write. I don't want to. I guess I'm going to have to. I'll have to work here. So zero. What's it on the? So I'm working on the. I'm working on calculating the homology. The homology group of the circle. So what's my zero chain? Every zero chain for the triangulation C bar 0 looks like what? He says A0 P0 plus A1 P1 plus A2 P2. That's a typical zero chain. All right? He says the boundary of a point is 0. So the 0 boundary map on C bar 0 is what? 0. All right. So that means, in particular, C0 is the 0 map. All right. Great. So what's the dimension of the kernel of boundary 0 map? It's equal to the dimension of the whole of C bar 0, right? The whole of C0 over the, I mean, it's 3. Okay? Now he says, okay, great. What's the most general one chain? Most general one chain, C bar 1, A, let's see his notation. I think he uses B's. B0, P1, P2, plus B1, P2, P0, plus B2, P0, P1. All right? And then what's he going to do? He says for some scalars bi, its boundary is what? Boundary of C1. This we can calculate, right? We've got like B0 times P2 minus P1 plus B1 times P0 minus P2 plus B2 times P1 minus P0. But remember, that's a zero chain. A basis for the zero chain are the vertices. So what you want to do is just look at like P0. P0 gets what? B1 minus B2. And then what's with B1? Well, with B1, what's with P1 rather? With P1, we've got B2 minus B0, I think. Yeah. And then what goes with P2? With P2, we've got B0 minus B1? Okay. And which boundary map is this? This is the one boundary map with my notation, right? Okay. So what's the matrix of the one boundary map? If we use, I need another Pac-Man, comma ghost. Pac-Man will be the basis P1, P2, P2, P0. I usually use beta for basis, but it's already used, P0, P1. There's my basis for one chains. My basis for zero chains, which is the codomain of this map, is going to be 0, 1, 2. So if you look at the matrix with respect to these choice of bases, what is it? What's that one? So I'm supposed to, I should look at like partial 1 of that. What is it? Are you giving me the first column? Or the first row? 0, minus 1, 1. That's because this is coming from the fact that the boundary of P1, P2, right, is P2 minus P1, which puts a 1 here, a minus 1 there, and a 0 there because there's no P0. This is linear algebra. And then the next up, for 2, 0, I think we get 1, minus 1, 0, and then for the last one we get I think I was wrong there. What would you say it was? 1, or minus 1?
Oh, I mean 1, 0.
I'm sorry, I'm an idiot. What is it? Is that right? This is right? I'm just checking. And that one gives me all right. So what's the rank of that matrix? I'll tell you one thing. It definitely doesn't have rank 1, right? And it definitely doesn't have rank 3, because if you calculate the determinant, you can easily see that it's 0. And in fact, if you stare at it for a second, you'll see that if you were to add, or if you were to subtract How's it go? Some way to get from one of these to the other. Add these two. If I add the last two, do I get the first one? If I add the last two, I get minus the first one. Right? So they're linearly dependent. So anyway, what I'm trying to get to is that the so if I put a 1 here, right? Then what happens? This is 3-dimensional, right? We just saw that the dimension of the kernel 1 is what? 1? And this happens to be 2. I guess that doesn't help me directly, but then what else do I know? So I guess I need to go back to what's H1K? It's what? Z1K mod B1K? Which is what? What's Z1K? That's the dimension, that's the kernel, right? Kernel of boundary 1, right? Mod what? The image of what? Boundary 2. Oh, I haven't calculated that yet, have I? Ah! Right, so what does that get for me? I think I'm looking at the wrong one. I should be looking at H0, right? If I'm looking at the 0th homology, what's the kernel of the 0th boundary map? Well, it's the 0 map. It's the whole thing. That's 3-dimensional. What's the image of the? We just did a bunch of calculations to prove that this has dimension 2. So that shows us dimension 3, dimension 2, by linear algebra, the 0th Betti number is 1. And if you look at the handout I gave you guys, he shows that it's actually going to be that the homology group for the circle, it's 1 when k equals to when m equals to 0. It's also 1 when m equals to 1. All right. If I just had another 5 minutes, we could explain it. It's not much more past where we are, and it's 0 beyond that. So that's the homology group for a circle, and that really describes topologically what the circle is. So if you have two different topological spaces, and they're homeomorphic, and you can calculate the simplicial homology, they must match. It's a topological invariant. Let me show you a homework I assigned Abstract 2 this semester, and then we'll be done for the break. In my defense, we were talking about interesting philosophy at the start of class. So I hope you guys don't mind me keeping you over for a couple minutes. I will try to stop soon because well, the snow has stopped, hasn't it? Yeah. So, listen, I have calculated everything I just did with you guys, and a little bit more I spread over 3 days of Abstract 2 this semester. Because I think it's an interesting example of the linear algebra involved. In particular, this gives us an example of a module, because really, I think you could do everything here with just integer coefficients. He says real coefficients, but come on. Do you need 2? Do you need a half? Is there anything in these constructions that requires real numbers? No. What's that? So it can be a what? Yeah, I mean, you can set up homology over other rings, but in particular, I think you could make do with integer linear combinations of M chain, of oriented simplices. Why doesn't he do that in this book? It's simple, because Rentland doesn't want to talk about a module, because that's not what his book is about. It's about manifolds. So it's just a better fit when because his ultimate goal is to compare the homology with the de Rham cohomology, which is built from differential forms, which is what that book is largely about. All right? And so there are various schemes. Well, not to use the technical term, but there are various strategies for calculating homology. There's simplicial homology. This is like probably the oldest one. That's very geometric and concrete. All right? By the way, if you look at the handout I gave you, if you look at the end of it, hopefully, I think I scanned a couple pages. He has a proof of that. You remember that theorem we had, maybe you saw it in high school, about the faces and the Euler number? Yeah, that actually is straightforward to prove using what we did today. You can actually calculate that from a little bit of linear algebra and the boundary map and all this jazz. In the statement of the Euler characteristic theorem, I mean, the Euler characteristic is the sum of the alternating sum of the Betti numbers. So the Betti numbers give you the Euler characteristic, among other things. This right here is the corresponding calculation of the homology of the two-sphere, which is triangulated by a tetrahedron. So I calculate the kernel and the image of the various boundary maps, all right? They are bigger, but after a little bit of linear algebra, you're able to show that H2K has dimension 1 in this case, and H, I think, let's see here, how does it work out? Oh my goodness, look at this. So many. Straightforward but tedious, right? And eventually I figured out, as anyone can, that for the two-sphere, the, solid, like a balloon, right? The homology is the reals for j equals to 0 and j equals to 2, and it's 0 otherwise. We just found that the homology was the reals for j equals to 1 and 0 for the circle. And more generally, you can show that the homology of an n-sphere is the reals for 0 and also for n, and it's 0 otherwise. So this is a mad digression from what we were doing last time, but I hope you appreciate it. I mean, this is the other side of algebraic topology, is the study of homology. And when you study this in abstract algebra properly, you'll spend a lot of time talking about homological algebra. Homological algebra is that picture I drew with the chain of subspaces, studying how you understand maps and how they filter through such diagrams. And it's a very beautiful and very, very general bit of algebra, which you haven't seen yet. So, I mean, there's a section in Dummett and Foote, but I usually tell people to skip it because it's really hard. And you got to save something for grad school, right? Yeah. Or the break. Let us begin the break. So.
Actually, I should prove